Good morning, dear students. Last class, I have finished different types of problems from mathematical induction, and I solved those problems all with help of three steps: basic step, induction step, and conclusion step. But today, I am going to solving different pattern type questions. I'll tell you today. Last class, they gave problems in the form of sequences like in series, but now today directly they will give some n-term formulas, n-term problems they gave here. Like those problems today I am going to solving. In these types of problems also we are going to using three steps: basic step, induction step, and conclusion step. Here in different ways we are going to using induction step here. I'll show you method of applying steps in case of solutions of different types of problems in the lesson principles of mathematical induction. Let us now we are starting that first question. Prove by mathematical induction. Prove by mathematical induction. Prove by mathematical induction. N into n plus 1 into n plus 5. N plus 5 is a multiple of 3. Is a multiple of 3. How we are going to solve it like all these questions now today we will discuss. Because before this in the previous classes we solved the problems, those problems the form of series. But for this question they are not giving any series here. Directly they gave one term here. Now we are going to showing this. This is a total n term is a multiple of 3. Multiple of 3 means 3 into something should get here. Multiple of 3, or we can call it as divisible by 3. For example, 6 is there. 6 is a multiple of 3. At the same time 6 is divisible by 3. That's what they may ask a question like this also. Prove by mathematical induction n into n plus 1 into n plus 5 is divisible by 3. Divisible by nothing but n into n plus 1 into n plus 5 is a multiple of 3. Multiple of or divisible by these two or these two both are giving same meaning here. Now we are going to give a solution for this question in 3 steps. Now we'll discuss about basic step first. Basic step. Basic step. Let P of n is true for. Let P of n is true for n is equal to 1. N is equal to 1. See here, in this case, n into n plus 1 into n plus 5. In this case, we are going to putting 1 here. 1 of 1 plus 1 into 1 plus 5 is equal to 1 into 2 into 6 is equal to 12. 12 can be written as 3 into 4, which is a multiple of 4. Which is a multiple of 4. Which is multiple of 3. Multiple of 3 because it is multiple of 4 also, but in the problem they are asking multiple of 3. That's what here we are going to writing which is a multiple of 3. That's why we give proof for in the case of n is equal to 1 also. Finally, you should get 3 into something, 3 into some one perfect number, that is one natural number. If you can get like that, easily we can tell about that, that is the multiple of 3. Here 12 we got, 12 can be written as 3 into 4, no, that's why, which is we can write multiple of 3. Now let us, we are going to giving proof for induction step. Induction step. Let P of n is true for, let P of n is true for n is equal to k. N is equal to k means instead of n we are going to put in k here. K into k plus 1 into k plus 5 is equal to 3m we are going to write it here. Because it for 12 we are going to write in 3 into 4. For 18, 3 into 6. For 30, 3 into 10. For 21, 3 into 7. Like that we are writing for multiples of it. But here we don't know which number is coming here. For that only we are going to writing here k of k plus 1 of k plus 5 is equal to 3m, where m belongs to n. M belongs to n here. Because we are discussing about the natural numbers only. Because like all these problems are depending upon set of natural numbers only. See if you can observe in case of exercise 4.1, like all those problems are defined on set of all natural numbers only here. 3m. Multiply it. K into k plus 1 is the k square plus k into k plus 5 is equal to 3m. And again multiply with k square and k. Start with the product with k square to these two terms. K square into k cube. K square into 5, 5k square. K into k square. Plus 5k into 5, 5k is equal to 3m. Next is k cube plus 5k square plus k square is 6k square plus 5k is equal to 3m. K cube plus 6k square plus 5k is equal to 3m. Send all these that side. Send these to the side. Then k cube is equal to 3m minus 6k square minus 5k. At the same time, you represent this equation number 1. But before this, in the previous questions, we added k plus 1 term on both sides of equation number 1. Because those questions are in the form of series. That's what we added k plus 1 term on both sides of equation number 1. But here, to like all these questions, no need of adding that k plus 1 term. Directly we are going to find the k plus 1 term. Instead of k cube, we are going to substituting this. Now I will show you how to solve that n is equal to k plus 1 also. Let P of n is true for, let P of n is true for n is equal to k plus 1. Here they gave n term n into n plus 1 into n plus 5. Instead of n directly we are going to substitute k plus 1. K k plus 1. Next k plus 1 plus 1. Next one is k plus 1 plus 5 is equal to k plus 1 into k plus 1 plus 1 is the k plus 2, k plus 6. Multiply these two here. K into k square, k into 2, 2k, plus 1 into k, 1 into 2, 2 into k plus 6. That is k square plus 2k plus k is the 3k plus 2 into k plus 6. Multiply with k square these two and multiply with 3k to these two, multiply with 2 by 2 with these two here. K square into k is k cube, k square into 6 plus 6k square, 3k into k, 3k square, 3k into 6, 18k, with 2, 2 into k, 2k, 2 into 6, 12. That is k cube plus 6k square plus 3k square, 9k square, 18k plus 2k, 20k plus 12. In k cube, for k cube, in equation from equation 1, what we have for k cube, bring and substitute in place of k cube here, is equal to k cube plus 3m minus 6k square minus 5k. Remaining terms as I should write 9k square plus 20k plus 12. Simplify this. 3m minus 6k square plus 9k square plus 3k square minus 5k plus 20k plus 15k plus remaining is 12. From all these, what we can take common here? 3 if we can take common, we will get here m plus k square plus 5k plus 4. 3 into some. 3 into something. 3 into some numbers means, some finite number means, definitely it is multiple of 3 or it is divisible by 3. We don't know that number, but finally we got 3 into or not. Should get the bracket part product with 3. Now the bracket part have product with 3. When it's have product with 3, easily we can tell it is the multiple of 3. At the same time, we can tell it is divisible by 3 also. That's what we give proof n is equal to k plus 1 also. But finally, write words like this. Which is multiple of 3? Which is multiple of 3? Which is multiple of 3? Therefore, P of k plus 1 is very points. Is very points. Next, last one is conclusion step. Conclusion step is same thing. What we have written that conclusion step to remaining questions. Same thing we are going to writing for this question also. What we have written conclusion step for previous questions. Same thing and same procedure we are going to writing for this question also. Therefore, the given statements The given statements is proved by the principles of mathematical induction, that is n is equal to 1, n is equal to k, and n is equal to k plus 1 for all n belongs to capital letter N here. But pattern is different. And before this, in previous questions, same we verified in case of basic step with n is equal to 1, and in case of induction step also we verified with n is equal to k, and verified with n is equal to k plus 1. But in case of k plus 1, we calculate how much we are getting k plus 1 term at the rough side of solution of the problem. After getting that, we added that k plus 1 term on both sides of equation number 1, and afterwards we solved, and finally we got the data condition. But in these types of problems, they are not giving directly series here. That's why if they can give like these questions, better apply this type of solution. N is equal to 1 is verified, n is equal to k. In case of n is equal to k only, highest power is equal to how much you are getting, that much you should write. At the same time, you represent that equation number 1. In case of n is equal to k plus 1, instead of n, directly can substitute k plus 1 and simplify it. In highest power case, what we have from equation 1, bring and substitute in that place, and finally we got multiple of that given number. Like that, we are giving solution to this question. Let us now we are going to solving another question. Prove by principles of mathematical induction 10 to the power of 2n minus 1 plus 1 is divisible by 11 divisible by 11 or multiple of 11, both are giving same meaning here. Divisible by 11 or multiple of 11, these two both are giving same meaning here. That's why before this question, what we applied procedure, same thing and same procedure we are going to applying for this question. First one is basic step. Solution for this question is basic step. Like P of n is true for P of n is true for n is equal to 1. N is equal to 1. 10 to the power of 2 into 1 minus 1 plus 1 is equal to 10 to the power of 2 into 1 2 minus 1 1 plus 1 is equal to 10 plus 1 is equal to 11. 11 can be written as 11 into 1, which is divisible by 11. Which is divisible by 11. Therefore, P of 1 is proved. Therefore, P P of 1 is proved. Next, induction step. Induction step. Induction step. Let P of n is true for. Let P of n is true for n is equal to k. N is equal to k. Instead of n, we are going to substituting k only. That is 10 to the power of 2k minus 1 plus 1 is equal to 11m, where m belongs to n here. Because we got 11, 11 means 11 into 1, 22, 11 into 2, 33, 11 into 3, 44, 11 into 4. Like that we are going to writing for all multiples of 11. Here we don't know which number we are getting here. That's what I am going to writing 11m. How we are going to writing 11m only means in the question they are asking it must and should divisible by 11. 10 to the power of 2k minus 1 is equal to 11m minus 1 here. At the same time, we represent that equation number 1 here. Next one is, let P of n is true for. Let P of n is true for n is equal to k plus 1. Is equal to k plus 1 here. Is equal to k plus 1. That is 10 to the power of 2 of k plus 1 minus 1 plus 1 is equal to plus 1 is equal to 10 to the power of 2k plus 2 minus 1 plus 1 here. That is equal to 10 to the power of 2k minus 1 plus 2 minus 1 is there. Just you can reverse them. Minus 1 plus 2 plus 1. That is, we can write this term like this: 10 to the power of 2k minus 1 into 10 square plus 1. 10 to the power of 2k minus 1 plus 2 is there. It can be written as like this: 10 to the power of 2k minus 1 into 10 square. Because if the bases are same, then we can add their powers. In 10 to the power of 2k minus 1 place, how much we have? 11m minus 1 in this place. For this place we can draw it from equation 1. 11m minus 1 into 10 square is the 100 plus 1. Multiply with 100. 11 into m into 100, 100 m. 100 into minus 1, minus 100 plus 1 cube. 11 into 100 m minus 99. From these two, what we can take common here? 11 take common. If we can take 11 common here, 100 m minus 9. And 11 into some number means, 11 into some perfect numbers means definitely which is divisible by 11. Which is divisible by 11. Which is divisible by 11. Therefore, P of k plus 1 is proved. And finally, you should write a conclusion step also. Conclusion step, next one is therefore the given statements therefore the given statements the given statements is proved by principles of mathematical induction that is n is equal to 1, n is equal to k and n is equal to k plus 1 for all n belongs to capital letter N. Like that we are going to writing induction step. And for this question also, first we verified with n is equal to 1. In case of n is equal to 1, we got 11. 11 can be written as 11 into 1. At the same time, in case of n is equal to k, we considered 11m here. 11m. 11m, the 10 to the power of 2k minus 1 is equal to 11m minus 1. And in case of n is equal to k plus 1, instead of n we substituted k plus 1 and we gave solution. In that solution, we got 10 to the power of 2k minus 1. Instead of that, from equation 1, we bring and substitute in case of 10 to the power of 2k minus 1 is 11m minus 1. On simplification, on giving the calculation part for this, finally we got 11 into 100m minus 9. 11 into some perfect numbers, 11 into something bracket part means it must and should divisible by 11. Divisible by 11 means we can call it as also multiple of 11. That's why both are given same meaning here. And finally we concluded, we have written concluding. In case of concluding step, it is therefore the given statement P of n is proved by principles of mathematical induction, that is n is equal to 1, n is equal to k and n is equal to k plus 1. Like that we have given solution for this question. Let us we are going to solving another question. Prove by principles of mathematical induction x to the power of 2n minus y to the power of 2n, third question, y to the power of 2n is divisible by x minus y here. X minus y. But divisible by x minus y means we must and should get x minus y into something. X minus y into something. Now we are going discussing about basic step. Basic step here. Solution. Basic step first. Let P of n is true for true for n is equal to k. N is equal to 1. First one is true for n is equal to 1. Say here x to the power of 2n minus y to the power of 2n is equal to x to the power of 2 into 1 minus y to the power of 2 into 1 is equal to x square minus y square. It is in the form of a square minus b square formula. is equal to, we can write x minus y into x plus y. X plus y. Now, which is divisible by x minus y, because x minus y have product with x plus y. Its have product with x plus y means easily we can tell which is divisible by x minus y. Which is divisible by x minus y. Therefore, P of 1 is proved here. Next, let us we are going discussing about induction step. Induction step here. Let P of n is true for. Let P of n is true for n is equal to k. N is equal to k here. That is x to the power of 2k minus y to the power of 2k is equal to x minus y into m. That is where m belongs to n here. Because why I am writing m belongs to n means in that exercise 4.1 all the problems are belonging to set of all natural numbers only. That's what here I have taken for m also natural number. X to the power of 2k is equal to x minus y into m plus y to the power of 2k here. At the same time, we represent this equation number 1. Now let P of n is true for n is equal to k plus 1 is true for n is equal to k plus 1 here. That is x to the power of 2 into k plus 1 minus y to the power of 2 into k plus 1 is equal to x to the power of 2k plus 2 minus y to the power of 2k plus 2 is equal to here is equal to x to the power of 2k plus 2 can be written as x to the power of 2k into x square minus y to the power of 2k can be written as y to the power of 2k into y square is equal to. In case of x power 2k already we have from equation 1 x minus 1 into m plus y power 2k. Bring and substitute in place of x power 2k. It is in place of x power 2k it is x minus y into m plus y power 2k into x square minus y power 2k into y square is equal to multiply these two terms with x square x minus y into m into x square plus y power 2k into x square minus y power 2k into y square is equal to x minus y into m x square plus, from these two terms we can take y power 2k common, then we will get here x square minus y square is equal to x minus y into mx square plus y power 2k into bracket part. It is in the form of a square minus b square formula. A square minus b square means what we can write? A minus b into a plus b. According to that, we can write for this x minus y into x plus y. Now what is common here? X minus y take common. Then we will get mx square plus y power 2k into x plus y, which is divisible by x minus y, because x minus y have product with the bracket term. When it is have product means definitely we can tell which is divisible by x minus y, which is divisible by x minus y, divisible by x minus y. Therefore, P of k plus 1 is proved or verified. And finally, we should write conclusion step. Conclusion step here. Therefore, the given statements. Therefore, the given statements P of n is proved by the principles of mathematical induction. Mathematical induction, that is n is equal to 1, n is equal to k, and n is equal to k plus 1. That is for all n belongs to capital N. N belongs to capital N. Same in previous problems, how we have written a conclusion step, similar in the same way should write conclusion step for this problem also. Like that today I finished like all these problems from mathematical induction. Next class also we will solve different types of problems based on these only, because before this in previous classes I solved series type problems, but in this we solved only directly nth term form problems only. Same problems next class also we will solve. In that class also we are going to giving proof to like all these questions with help of 3 steps: basic step, induction step, and conclusion step. Like those questions next class we will solve. Thank you very much.